When we look at evaluating radical exponents for Honors Math 2 Section 0.2, we really start to get the idea of simplest radical form. And you have seen in the past your basic square roots, like the square root of 16, square root of 25, square root of 144, and you've simplified them because they were perfect squares. They just became what their square root was. So for example, 16 is 4 times 4, and that becomes the square root of 4 squared. The square root and the squared give us a 4. 25 is 5 squared, so it comes out to be 5. 144 is 12 squared, it comes out to be 12. So we're going to go further now. What if it wasn't a perfect square and we had to simplify it? So let's take a look at something like square root of 32. Now I do not have it as a perfect square. It's actually between 25 and 36, so we could guess it's between 5 and 6, but we're not going to say that. We need to find a better result. Plug it into a calculator and give it in a decimal is not an exact answer because it is an irrational number. We want to find the best, most accurate way to represent it. So if I look at 32, and I want to take the idea I kind of did over here, 32, I can write factors in a variety of ways. I could say 2 times 16. I could say 4 times 8. Well, really, I could just say that either of those two. Now, if I'm looking to factor it, though, I like 2 times 16, because 2 times 16 is really 4 times 4 times 2. So whereas we went 2 times 4 squared, I know 4 squared inside the square root gives me 4. What I can do is take that out, and it just becomes a 2, and my answer is, let's make that 4, is 4 root 2. So I can now say that the square root of 32 becomes 4 root 2 because it's the square root of 16 times the square root of 2, and the square root of 16 just becomes 4. So it's breaking it down and looking for these pairs. So anytime we see a square root, we want to make a pair of common factors, and that pair is the ticket out to bring a single term with it. So let's try that again. Let's kind of work through the process here. So if I have 72, 72 is 36 times 2. Now you may be saying, what about 9 and 8? And we'll look at that one in a second, but let's look at 36 and 2 first. Because why I like 36 is that's 6 times 6. Here's a pair of common factors. Those pair up to go out of the square root. So really it's like saying 6 times 2. Pairing those up, they come out as one term, and we're left with 6 root 2. So the simplest radical form of the square root of 72 is 6 root 2. We find a pair, we take it out. Now, let's look at 72 again, but probably go with maybe the common one you would think of, 8 and 9. Now, 9 breaks down to be 3 and 3. 8 is 2 and 4, and these become 2 and 2. So you may be looking going, well, that's completely different factors than you had. Well, kind of. We just happened to stop at the 6s. But here I have 3s, here I have 2s, and that lone 2 left over. So that means the 3s can come out, the 2s can come out, and when they come out as a pair, they end up as 1 on the outside, and I'm left with the lone 2 on the inside. Now 3 times 2 gives me 6 root 2, which was the same result as I got the first time. Let's do another one. Let's say we had, let's go 98. Well, 98, we got to sit here and look at some factors. We could do 2, because it's even. And so half of 98 is 49. And really, anytime you're not sure about the factors, if it's even, try 2. If you can look for 3s or 5s, it's just something to start breaking it apart. Even if it's a very large number and that's not the best factor, if you keep working with it, you'll find something that works. Now 49, though, becomes 7 and 7. So those get paired up, a pair of those come out, and I'm left with 7 root 2. Now, does it work every time? No, not quite. The simplest radical form, sometimes if we had something like the square root of 15. Square root of 15 is 3 times 5. Neither of those have a pair. Neither of those are perfect squares in themselves, so it just stays as the square root of 15, and that is simplest radical form. What you have to look at is when you have terms that it is possible to take out a perfect square, it is possible to find that pair and take them out. Now we're not just going to limit ourselves, though, to numbers. We can also look at variables. So let's say we had the square root of a squared b to the 4th c to the 7th. So I'm going to just kind of write these all out. So I got a, b, 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 c, 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 c. All right, so I need a pair of them to come out. Well, a squared in the square root, one of them comes out. I'm going to have an a on the outside. I have one set of b's, two set of b's, or really b squared squared. Those come out to be 2. So when it takes 2 on the inside to get 1 on the outside. Now C, I have 7 of them. So I'm going to have 1 pair, 2 pairs, 3 pairs. So I'm going to have C to the 3rd on the outside, but I have that 1 left in. That's okay, it's just left right there. So I'd say a b squared c cubed times root c, or the square root of c. Now, we can take that and go a little bit further. So let's now say we have something like the square root of x to the 3rd. Now, we kind of looked there when we had the odd number with c just a minute ago. That has x squared times x. Well, the square root of x squared brings this out, so it's left on the outside with an x inside. But what if we went a little bit further? What if I said the 4th root of x to the 5th? And this is a bit of a jump. Now, the idea stays here. Whenever I have square root, it's really like having a 2, but we don't write the 2. We need, it's opposite of the squared. It's the reciprocal operation to it. So we don't have it, but there should be a 2 there. Okay? Now this is saying I need the 4th root, so I need 4 of something to take 1 out, or the 4th of it. Well, if I have 5 x's and one set of 4 is enough to take it out, or like saying x to the 4th times x, this comes out and I'm left with an x inside, so that'd be the x times the 4th root of x. So really what root it is, either square root, 4th root, or whatever power, it allows us to start simplifying. Now what if we did something like the 4th root of x to the 3rd? This does not have 4 of them. I can't simplify that, so that is actually the simplest form. So we take that and let's start throwing some things together here. So let's go 80 x to the 3rd y to the 6th. So I'm first going to look at 80. I want to get that to the simplest form. The variables, they kind of take care of themselves because we know how many we have of them. So 80, let's see, we could do something like 8 times 10. 10 is 2 and 5. 8 is 4 and 2. And we have 2 and 2. So I've gotten down to all the prime factors. It's 2, 2, 2, 2, 5. I look for pairs. I got a pair of 2's here, a pair of 2's there, and a 5. So now these come out. I got a 2 on the outside, a 2 on the outside, and then a 5 left inside. I'll put them together in a minute. Okay, so that takes care of 80. X to the 3rd is I have 1 pair, so that comes out, 1 pair left over. It's kind of the remainder. It's the 1 left extra that didn't come out. The x squared comes out, becomes an x. Y to the 6th, I have 3 sets of 2. So with 3 sets of 2, I have 3 on the outside. So my answer here is going to be 4xy cubed times the square root of 5x. Now I kind of like the values I have here to start. Let's think of what if it was a 3rd root. So 80x cubed y to the 6th. I already know the factors of 80 is 2 times 2 times 2 times 2 times 5. So if I'm looking at the 3rd root, or the cube root here, I need a set of 3 to bring it out. So I have 1 set here, that comes out, and what's going to be left is the 2 and 5, which I'll just put back together and make 10. I have an x to the third. Well, I need 3 of them together to punch their ticket to bring it out. I have 3, makes it just an x on the outside. It's really how many sets did you have to meet that. Y to the 6th, how many sets of 3 do I have? I have 2, exactly, so y squared comes out. So that's 2x y squared times the cube root of 10. Let's use this set of numbers one more time and go now 4th root. So again, 2, 2, 2, 2, and 5. So I need 4 of them, a set of 4 to bring it out. Or how many sets of 4 do I have? I have 1. So 1, 2 comes out. It looks like 5 is going to be left in. Do I have any sets of 4 for the x's? Nope, I only have 3. Wasn't enough. They stay inside. Y to the 6th, I have 1 set. So 1 set comes out of 4. That leaves me 2 left over. So we're going to write 2y times the 4th root of 5x cubed y squared. So really, the idea, whatever root I have, whatever power that is, it's just really how many sets I have. So as we go through and simplifying this, looking at factors and looking at the variables, you're just counting the number of sets you have. Those come out, and if you didn't have a full set, that just remains inside. So let's look at something like the 4th root of 144x to the 6th. So if we look at the factors of 144, it is 16 times 9. Now, if that was the square root, we'd know it's 12 and 12, and we'd have that. But this is now 4th root. So I got 3's. 16 is 4 times 4. Got some 2's here. It breaks down. So the factors of 144 are 2, 2, 2, 2, 3, 3, or 2 to the 4th and 3 squared. So I need a set of 4 to come out. I have 1 set of 4s of 2's, so that will come out. 3's, oh, sorry, I'm too short, so the 3 squared, or 9, is going to stay inside. We'll just write 3 squared for now. X to the 6th, how many sets of 4 do I have? I have 1, so that comes out. And I have 2 left over. They stay inside. So my answer becomes 2x times the 4th root of 9x squared. Let's go cube root of 216, x to the 12th, y to the 7th, z squared. So 216 is actually 6 to the 3rd. So that actually makes things easier for us. Well, how many sets of 6 do I have? I have 1. That comes out. X to the 12th, how many sets of 3? I have 4. That comes out. That goes evenly, so none left inside. Y to the 7th, I have 2 sets of 3, so y squared comes out. But that's only 6, so I have 1 left. Y stays inside. Z squared, I don't have a set of 3, stays as it is. So I get 6x to the 4th y squared times the cube root of yz squared. Now let's look at one more here. Let's do something like 5 times the square root of 320 m to the 10th. So it's square root again. Now this 5 out in front is just like a coefficient. I'm multiplying by 5. Whatever I do and take care of here, I'm just going to multiply by 5 on the outside. So let's start looking at factors of 320. It is 32 times 10. 32, have we factored that one yet? We did. Down below we found that was 4 root 2. So this one was actually 16 times 2, and we have a 2 and a 5. So looking at these factors. Now I know this is going to be 4 and 4. I'm not going to break the 4's down. I got 4's, I got 2's. So the 4's come out, the 2's come out. What stays in is the 5. So same as before, I got a set of 4s, set of 2s come out, 5 stays inside because it's the factor. Now the 5 that originally was there is outside here as well, but it's like we're doing everything first inside the radical, then we'll worry about the 5. Now m to the 10th, it's not how many sets of 5, it's how many sets of 2 that I have because it's still the square root. So I have 5 sets of m, of 5 sets of 2 of m when I have m to the 10th, so that comes out evenly. I have nothing left inside. Now I'm just going to put this together. 2 and 4 is 8, and 5 is 40, so 40m to the 5th root 5.